So I want to come back and talk a little bit about the spectrum that we see from hydrogen as well as other atoms. And if we could take different elements and put them into sealed tubes and put a high voltage across them, then we're going to see light. And more importantly, we're only going to see light at certain discrete wavelengths, and that's going to depend upon the gas that we have put inside the tube. Now, we do call this the line spectrum, and essentially 19th century physics couldn't explain why they have to be different. And so, as I said, for hydrogen we're going to have some UV, some visible, some red, and some infrared. Sodium is going to look, well, it's going to have a lot of yellow, and this is just kind of showing the visible portion of the spectrum. Helium is going to look a little bit different. This is going to be neon, this is going to be mercury, and this is kind of like a fingerprint for whatever we're looking at, and every single one will be different. And kind of the reason for that is because hydrogen is going to have certain energy levels that are going to be different from the energy levels of sodium, and hence different wavelengths, different than the energy levels of helium, and so on and so forth. So no two elements will have the same exact line spectrum. Now, it also turns out that we can talk about absorption spectra, which is going to be the exact opposite of a line spectrum. And if we were to shine some light through a gas, and in this case I'm going to go ahead and put my hydrogen gas inside of that guy right over there, and we were to look at the light that comes out the other side, just like hydrogen is going to emit these wavelengths, that's the emission spectrum, it's going to absorb these wavelengths, those same exact wavelengths, and those wavelengths only. And kind of what's going on is if we have these energy levels of hydrogen, and if an electron hops down and emits a photon of a certain color right here, or if it hops down right here, it's going to emit a certain photon. It would also make sense that we could excite an electron, and as we had an incident photon coming in, it's only going to be excited by the photon that carries the same energy as this energy difference, or this energy difference, or that energy difference. And so the frequency really matters when it comes to absorption. And it was Niels Bohr who actually explained this. He's the one that said that there has to be these discrete energy levels inside of an atom. And when an atom makes a transition from one higher energy level to a lower energy level, that energy is going to go into emitting a photon. And so here we'd have an electron that's in some higher state. It's going to drop down, and the frequency is related to the energy difference. And the same exact true is going to apply when we have the absorption of a photon. Only a photon that has just the right energy is going to cause this electron to go from a higher frequency, or from a lower energy state up to a higher energy state. And so it was Bohr who first was able to explain this spectrum for hydrogen, and he worked his way through all of the details where he could actually figure out what the radius needed to be, and also he realized that orbital angular momentum had to be quantized, and so we could actually say orbital angular momentum is going to be n times h bar, where that's n h over 2 pi. And n is going to be what we call the principal quantum number, and you're going to see that guy quite a bit here. Now, Bohr also worked out the radius, or the radii that he was to expect, and actually we pull this n out right over there. This a naught is actually called the Bohr radius, and that's kind of all these other constants. And what Bohr kind of worked itself out was it was about 5.3 times 10 to the minus 11th meters, and that's kind of consistent as to what people knew the size of an atom ought to be. And Bohr also said that the energies had to be quantized. I gave it to you in joules earlier, but it's going to be negative 13.6 electron volts divided by n squared, where again n is the quantum number and n equals 1 would be the ground state. And so he was able to explain why Balmer was able to predict certain lines. Now, it does turn out that the Balmer series is not the only series of lines that we're going to see off of hydrogen. It's just the ones that we're most likely to see because it's in largely the visible and some UV wavelengths as well. And in these cases, we're kind of dropping down from some excited states, so n equals 6, 5, 4, and 3, all the way down to the n equal 2 orbit right over here. As we drop from other orbits down to, say, the n=3, we're going to see some infrared, and those are going to be these series right over here. And when we drop down to the n=1 state, then we're going to see the Lyman series, and again, we're talking about higher energy differences, so we would expect it to be in the ultraviolet. And the reverse is also going to be true, where if we wanted to excite an electron, then it's going to take a certain amount of energy, and it's going to be a discrete amount of energy. Now, one important form of energy I want you to realize is we can talk about something called the ionization energy, and that's when we're going to have an electron in the ground state, and if we had a photon come in, it's got enough energy to ionize this atom, which essentially means take this electron and knock it totally out of the atom. Now, since we know that it's in a well, and that well is 13.6 eV deep, to ionize a hydrogen atom in the ground state, it would take 13.6 electron volts. If it was sitting, say, in the n=2, then it would take 3.4 electron volts. And it would definitely take some ultraviolet light to do this. And actually something else to keep in mind is if it had more energy, then it could knock it out and give it some kinetic energy. Now, do keep in mind that we have lots of other atoms out there, and we largely talk about hydrogen because it's the simplest. It's got one proton and one electron, and the energy levels can be understood fairly easily. We can talk about other things, such as helium. Helium is slightly more complicated than hydrogen. Helium is going to have its own energy levels, and that's dictated essentially by the fact that it is helium, and it's got its own energy speeds and all that good stuff. And because these energy levels are different than that of hydrogen, then helium is going to have different delta E's and hence different wavelengths associated with it. Now, I do want to talk a little bit about spontaneous emission versus stimulated emission, which is kind of related to absorption. If we had some light that was incident upon some atoms, then it can excite them, and it's going to essentially absorb that light, and so it's going to take an electron and increase it up to a higher energy level. And when the electron is spontaneously allowed to decay, so the electron jumps down just like that, and it's going to emit a photon that has the corresponding frequency. You can kind of see that guy right over there. Now, it turns out that if you have a whole bunch of electrons that are in this higher energy level, it's actually called a population inversion, then if you were to kind of seed this and just send in a wavelength of just the right energy, then all of these electrons can jump onto the bandwagon, so to speak, and we can stimulate them into emitting their own photons, and we can get a whole lot of photons, a whole lot of light coming out of the end of this guy. This is actually the basis for a laser. Now, I do know enough about lasers to be dangerous, so if you want to talk about how we can get to population inversion, then we can talk in class. But I just want you to kind of know that this exists, but there's not a lot that we can do with it at this level of physics. So up until this point, we've talked about gases that can emit single distinct colors of light, distinct wavelengths. And I like to think of this as just ringing some bells. If I had 3 different bells and they had they were made very well, then they would have very distinct frequencies and hence wavelengths. However, if I took all these guys and I chucked them into a box and I shook it, then it's going to sound, well, not nearly as pretty. And essentially this is going to be the way that solids behave when they emit light. If you think about it, a solid is going to be a whole bunch of different atoms that are bonded together by some chemical bonds, and when solids emit light, it's going to be like a bunch of different bells which have their own frequency shoved into a box. So if we look at what wavelengths would come off of a black body, which is essentially just going to be a really hot, dense object, so think like a red-hot glowing nail or something like that, we're not going to see just a single frequency, we're going to see what's called a continuous spectra, or a bunch of frequencies. And this is kind of like having a bunch of tuning forks that you shove into a suitcase or something like that. Now, it does turn out that the temperature matters, and I'm probably not telling you anything that you don't already know. you know that if something is kind of glowing hot, or if something is hot but you can't see it glowing, then it's emitting in the infrared. And if we were to take a look at the intensity that comes off of a black body as a function of wavelength, then it's going to kind of peak, and as we increase our temperature, so work our way just like this, then we're actually working our way from out here in the infrared all the way up to the ultraviolet. Now, it does turn out that classical physics predicted kind of this little portion of the spectrum. However, we had something called the UV catastrophe, where we said as wavelength keeps on increasing, that the intensity would increase as well. And so that was actually a bad thing. That's not the way the world actually works. And it turns out it took Max Planck with quantum physics to explain why that didn't actually happen. Now, I won't give you the equation that Planck derived, but I will talk very quickly about kind of the peak wavelength that we might see. And that peak wavelength actually uses something called Wien's displacement law, which is going to predict the maximum wavelength. So the maximum wavelength multiplied by temperature is going to be equal to 2.9 times 10 to the minus 3, and it's going to have a unit of a Kelvin multiplied by a meter. And that's just a way to predict, again, the maximum peak of this black body curve. So let's go ahead and figure out what the maximum wavelength we would expect to get from our sun, which is essentially a black body. That's going to be 2.9 times 10 to the minus 3 divided by the temperature of the sun, which is going to be 5800. And so we're going to get a wavelength of roughly 500 nanometers or so. So I do want to finish off by saying that if the Heisenberg uncertainty principle works for light particles, then it has to work for other particles as well. And so the uncertainty principle based on position and momentum, or delta x multiplied by delta p, has got to be equal to, or larger than or equal to, h bar over 2, and that of energy, delta t times delta E, has got to be larger than or equal to h bar over 2, also applies to electrons as well. And as if we sent some electrons through two slits, then it's going to behave just the same way light will. And as we increase our knowledge of where these electrons are going, so if I were to say decrease the slit separation, then the momentum has to go up. So electrons are going to behave just like waves will. And if we were to look at the electron interference pattern, then just like light, it's going to build up essentially electron at a time, and it's going to look kind of granular. So after 28 electrons, we might observe something that looks like this. And after 1,000, and after 10,000, we're going to start to build up to the expected interference pattern, where we're going to have bright bands and dark bands where the electrons have and have not impacted.